Hello everyone, welcome back. In this particular video, we're going to continue with our discussions on the ring opening of epoxides under acidic conditions. In our previous video, we saw that similar to a basic or a nucleophilic condition, epoxides, because of the ring strain, they would open under acidic conditions. So let's say if you have some acid and you're in a nucleophilic solvent like methanol, then the epoxide ring would open up to give us an alcohol with an ether on the other side. Okay, so two functional groups, an ether and an alcohol. If it is a hydronium ion here, then your product is ethylene glycol. So because of the ring strain, again, the epoxide ring has this propensity, has this tendency to ring open under both acidic and nucleophilic conditions. What we're going to do in this video is continue with our discussions on the acidic, on the ring opening under acidic conditions, with a special emphasis on the regiochemistry of the reaction and the stereochemistry of the reaction. So what are some regiochemical outcomes and stereochemical outcomes of this ring opening? So for this purpose, we're going to choose two different epoxides because there is there's some difference in reactivity that's observed depending on the epoxide that's used. So if we have an epoxide where we have one of the carbons as a primary carbon, okay, and the other carbon as a secondary carbon. So we have a primary carbon here, and we have a secondary carbon over there. Under with this epoxides, under similar conditions, if we do the ring opening under acidic conditions, and if we have a nucleophilic solvent like methanol, now this could be any other nucleophile. I'm just using methanol as an example. Okay, under these conditions, it is observed that the product that's formed finally is going to be the alcohol here and the methoxy group over there. So what we notice is that the nucleophile attacks the less substituted carbon. So very similar to what we observed in case of a nucleophilic attack. The nucleophile has attacked the less substituted carbon. And this can be explained based on steric reasons. Okay, so steric reasons can explain this because when the nucleophile is attacking, it is attacking the less hindered carbon. That is what it's doing. Okay, what if our epoxide, or what's been observed is that if our epoxide has a secondary carbon, so I'm going to keep that the same, it's secondary on this side, on the left-hand side, and a tertiary carbon, let's say. So I'm going to draw in an epoxide where there is a secondary carbon and a tertiary carbon in the epoxide. In this particular case, it is observed that under similar conditions, the product that's obtained is one where the epoxide attacks the nucleophile attacks the epoxide at the more substituted carbon. So the product that we obtain is this compound. Okay, so if you notice, in the first case, the nucleophile attacked the less substituted carbon, So the attack is guided by sterics here. Whereas in the second case, the nucleophile attacks the more substituted carbon. Okay, the nucleophile is attacking the more substituted carbon. Why would that be so? Because the first example we can explain based on sterics, because the attack of the nucleophile was an SN2-like attack, so that would make sense. But in the second case, there is sort of an ambiguity here, okay? That the nucleophile is attacking the more substituted carbon. So this observation is explained on the basis of electronic reasons, okay? Electronic reasons can explain this observation. To understand the origin of this regiochemistry where the nucleophile attacks the more substituted carbon, we have to go into the mechanism of the reaction a little bit. So the mechanism of this reaction, if I were to write down a couple of steps here, it starts with the protonation of the epoxide oxygen. So the epoxide oxygen can get protonated because we are under acidic conditions. And when that happens, it's going to give us a protonated epoxide, okay? It's going to give us the protonated epoxide where this oxygen is now protonated. The secondary carbon has a methyl group on a wedge. The tertiary carbon has an ethyl group on the wedge and a methyl group on the dash. Okay. Now, in the epoxide to start off, or in any epoxide to start off, realize that the carbons that are connected to the epoxide oxygens, these are going to have a partial positive character to them. And that's because the oxygen is an electronegative element, it's going to have a partial negative character to it. Now, when this epoxide oxygen gets protonated, that's going to enhance the electron withdrawing ability of that oxygen. The oxygen is going to withdraw electron density more aggressively because it's an electronegative element and it has a formal positive charge on it. And what that's going to do is that's going to enhance the partial positive character of these two carbon atoms. Now, the big question is, are these two carbon atoms going to have a partial positive charge to the same extent, or would they have the same degree of a partial positive character? And realize that there is a difference in the nature of these carbons. One is a tertiary carbon and the other is a secondary carbon. So the answer is no, okay? The tertiary carbon, which is the more substituted carbon, okay? So the more substituted carbon is going to have a more pronounced partial positive nature to it. Whereas the secondary carbon, which is the less substituted carbon, is going to have a smaller partial positive nature to it. And that's because this is a tertiary carbon, so it can hold or it can stabilize that partial positive or the positive character better. Okay, it can stabilize that positive charge better. And you can imagine that maybe the structure can also be represented by something like this, where there is an oxygen with a hydrogen on it. It has one lone pair on it. And we have the methyl group. There's the ethyl group and the dash. And the two electrons in this bond are like closer to the oxygen now. There is an interaction here between the lone pair and that bond. So there is a positive charge on it, or like a more formal positive charge on it. And that positive charge is going to be better at that more substituted carbon. Okay, so there is basically a pronounced positive charge on that carbon. Or in simple terms, that carbon is now more electrophilic, okay? So that carbon is more electrophilic. And so because of that, what happens is the nucleophile attacks that carbon, because when the nucleophile is approaching to make that attack, it sees a bigger it sees a bigger positive charge over there. So the nucleophile goes and attacks that more substituted carbon. So that is why when you have an epoxide with a combination of a secondary and a tertiary, the nucleophile attacks that tertiary carbon instead of the secondary carbon. Now, the same case or the same scenario would apply to an example where you have a primary carbon and a tertiary carbon. The nucleophile is still going to attack the tertiary carbon because the tertiary carbon would have a more pronounced positive charge to it, which is going to facilitate that attack. That carbon is going to be more electrophilic. Okay, so that was the stereochemical aspect of epoxide ring opening. When you have an epoxide that contains a primary carbon versus a secondary carbon, the nucleophile attacks at the less substituted carbon. The attack is guided by sterics. When you have an epoxide which contains a tertiary carbon to it, then the attack happens at the more substituted carbon, and the attack is guided by electronic factors because that carbon has a more pronounced positive charge, which means it has a more electrophilic nature to it. So now we can use these same examples that we used for understanding the regiochemical outcome of epoxide ring opening under acidic conditions to understand the stereochemical outcome as well. Now, I've sort of summarized the stereochemical outcome of these reactions, of these epoxide ring opening reactions. The ring opening results in the inversion of configuration at the site of attack. That is key. So it results in an inversion of configuration at the site of the attack. So let's understand that term here, or let's understand that statement in these examples. So in our first example, where we had a combination of a secondary carbon and a primary carbon in an epoxide, the attack happens at the primary carbon. That's why the methoxy is connected to that primary carbon. And so the secondary carbon is not attacked, that's untouched. And so if you look at it, the secondary carbon is an R configuration to start off in the epoxide. I've assigned priorities to all four groups around that chiral center. So it's of an R configuration to start off, and it is of the R configuration in the product. So since the nucleophilic attack or the attack did not happen at that carbon, the configuration is retained. The primary carbon which is attacked is actually is not a chiral center. Okay, so we don't have to worry about the stereochemical outcome at that carbon. Let's go to the second example. This is an example where we had a combination of a secondary carbon and a tertiary carbon in an epoxide. And if you assign stereochemistry to the two carbons, now both carbons are chiral centers here. The secondary carbon is of an R configuration, very similar to the example of the top. And the tertiary carbon comes out to be of an S configuration. Okay, so this is an S configuration. So, and what we know is under these conditions, the nucleophile attacks the tertiary carbon. So when we look at our product, the secondary carbon continues to be of the R configuration. There's no change over there. The configuration is retained. But the tertiary carbon, which is attacked, there is an inversion of configuration of that carbon. It was an S configuration to start with, and now it is an R configuration. So that sort of summarizes or captures that statement. It says that the ring opening results in an inversion of configuration at the site of the attack. Now also recollect that this observation is the same as what happens under nucleophilic conditions or under basic conditions. So when a nucleophile goes and attacks the epoxide under basic conditions, the stereochemistry is inverted at the site of the attack. The carbon that's not attacked, that retains its configuration. So I hope this video here sort of captures and summarizes the stereochemical and the regiochemical aspect of epoxide ring opening under acidic conditions. Bye.